Okay, let me take up another MOS transistor as a switch, which is nothing but transmission gate. As the name suggests, a gate which transmits the input to the output. That's why it's called as transmission gate. And this transmission gate is realized in order to overcome the limitations of pass transistors. Of course, we have two types of pass transistors, a PMOS pass transistor and NMOS pass transistor. It is having its own advantages and disadvantages. And the limitation with respect to PMOS pass transistor is it's going to provide weak logic 0, and with respect to NMOS is it provides weak logic 1. And to overcome this limitation, a transmission gate has been introduced. This is nothing but the parallel combination of both a PMOS transistor and NMOS transistor. Therefore, whenever we have parallel combination of both PMOS and NMOS, either of the transistor will be in conducting state, providing both good logic 1 as well as good logic 0. As we are using both PMOS transistor and NMOS transistor, whatever the control voltages we need to apply, that should be able to drive both PMOS and NMOS transistor into on condition, and which are nothing but 0 volts and a VDD. And that's why it requires a dual rail, both true and its complement form for a control signal. And this is the symbol of a pass transistor. You can observe here we have a NMOS pass transistor and a PMOS pass transistor, which are connected in parallel. In order to drive this PMOS into on condition, and the control signal should be 0 volts, and to drive NMOS into on condition, the control signal should be VDD, and that's why it requires a dual rail. Both the normal form and the complement form is required in order to drive both the transistors into on condition as the control signals. And of course, both the inputs 0 and VDD can be transferred as such, 0 and VDD. And this is the input output combinations of a transmission gate. Let the control signal be 1 for PMOS, that is VDD for PMOS, and 0 volts for NMOS, which drives both PMOS and NMOS into off condition. Therefore, both will act as open circuit. Therefore, no input will be passed on to the output. Therefore, irrespective of the input 0 or VDD or logic 1, the output is said to be at high impedance state. Or else, whatever the previous value that is there before the switching off condition of this transmission gate, and that is going to be seen at the output of the transmission gate. Now let me drive the transistor into on condition by providing a logic 0 and logic 1 for PMOS and NMOS respectively as control signals. Therefore, for PMOS 0 and for NMOS N, when the input is 0, as both the transistors are in on condition, of course the output can discharge up to VTH for PMOS transistor. Whenever the output just reaches VTH, the PMOS goes into off condition, but still NMOS will be in on condition, providing a short path for the output node to the input node, and that's how we are able to achieve exact 0 volts at the output, and that's why the output is going to be whatever the input that is applied. Now for the same condition, PMOS 0 and NMOS 1, both the transistors will be in on condition, and whenever we go with the application of logic 1, for 0 and 1 case, both the transistors will be in on condition, and of course output can reach up to a value of VDD minus VTH in case of NMOS pass transistor, after which the NMOS goes into off condition, but still the PMOS will be in on condition. As the PMOS is in on condition, providing a short path for the output to the input, the output can reach up to VDD value. Fine. And that's how we are able to overcome the limitations of pass transistors and able to achieve both good logic 1 and good logic 0 for transmission gate. Fine. And the contribution of each of the transistors is said to be different at different situations. In order to understand the operation in detail, let me consider some specific cases. Try to consider the operation of the transmission gate under two cases. One is said to be large capacitive load and the other is said to be small capacitive load. And what is the difference between these two cases means, whenever I talk of large capacitive load at the output node, the output is going to slowly change from one logic level to another logic level. Whereas in the case of small capacitive load, the output is going to change instantaneously or with less amount of time in order to change from one logic level to another logic level. Now first let me consider the case where the input is changing from 0 to VDD and the output is going to have very large capacitive load. Right? Therefore input has instantaneously changed from 0 to VDD. As the output is having a very large value of capacitance, output is not going to change instantaneously from 0 to VDD, rather it's going to charge linearly. Therefore the output is going to be at 0 volts, after which linearly it's going to change in this fashion and finally it's able to reach a VDD and it's going to remain constant. And depending upon the output voltage, as the output is going to continuously change, there will be three different regions of operations with respect to these transistors. And we have three regions, and in these three regions let me tell you how the PMOS and NMOS are going to be and what about the output. Fine. And the region 1 is said to be where the output is going to be equal to or less than the threshold voltage of the PMOS transistor, and the region 2 is going to be between the threshold voltage of PMOS transistor and VDD minus the threshold voltage of NMOS transistor, and the region 3 is said to be the output at which the output is greater than VDD minus VTH. Why I am talking of these three regions means your output is linearly changing. Therefore, up to one specific part, your two transistors will be in one specific region of operation, and in the other voltage value, at other voltage value, the transistors will be in different operating regions. Therefore, in region 1, where the output is less than the threshold voltage of the PMOS transistor, both the transistors will be in saturation. And in second region, where the output is between VTP and VDD minus VTN, PMOS will be in linear region and NMOS will be in saturation. And in the third region, PMOS will be in linear and NMOS will be in cutoff condition, where the output is said to be VDD minus VTN. Now let me write the expressions of VDS, VGS so that we can able to understand the region of operations of the transistor and how the currents are going to vary and how the resistance are going to vary in case of pass transistor. And in region 1, both NMOS and PMOS are in saturation. Or let me try to define the potentials with respect to PMOS and NMOS transistors. Fine. First I am writing with respect to NMOS transistors. Therefore the potential difference between drain and source. Fine. Before considering that one, let me tell you, we have applied a voltage which is changing from 0 to VDD. At the input side, the input changes instantaneously. Therefore at the input side we have VDD, and at the output side we will have the output changing linearly. Fine. 0 to VDD. Therefore at this particular drain part of the NMOS transistor we have VDD, and on the other side we have output voltage. Therefore VDSN is equal to VDD minus V output. Similarly VGSN, fine. Gate terminal is this one and source terminal is this one. Therefore VDD minus V out. Similarly, let me talk of PMOS transistor, VDSP. And for the PMOS transistor, the terminals will be reversed. Therefore this is the drain terminal and this is the source terminal. Therefore VDSP is equal to V out minus VDD, and VGSP is equal to 0 minus VDD, and that is simply minus VDD. And in first region of operation, if you are able to substitute V out to be a VTP, then definitely both the transistors will be in saturation. And we all know the drain current expression in saturation is kW by L into VGS minus VT whole square. Therefore, let me write the current expressions of both NMOS transistor and PMOS transistor, and that is, as for NMOS transistor, it is simply Kn Wn by Ln in order to specify this for the NMOS transistor. And here the expression is VGS minus VT whole square. What is the VGS of NMOS transistor? It is simply VDD minus Vout. If at the place of VGS, simply write VDD minus Vout minus VTN whole square. Similarly, the drain current of PMOS transistor in switches saturation. Therefore, if we can simply write it as kW by L into VGS minus VT whole square. Therefore, what is VG? It is simply minus VDD minus VTP whole square. There won't be 2 here. Sorry. Now, those are the current expressions, and from those current expression, let us try to write the expressions for resistances. Fine. The equivalent resistance of the two transistors. The NMOS transistor resistance, I am going to represent it as R equivalent N, and similarly for PMOS it is R equivalent P. Fine. Therefore, R is nothing but voltage per current. Therefore, the input to output difference is VDD minus Vout divided by the current through the NMOS transistor, and similarly the same goes for PMOS transistor, input to output voltage VDD minus Vout by IDSP. Fine. Therefore, if you are going to substitute the same, VDD minus Vout by IDSN expression, and similarly VDD minus Vout by IDSP expression from the previous slide. And using these expressions, let us try to plot for currents and voltages. And similarly, in region 2, PMOS is in linear and NMOS is in saturation. Therefore, NMOS resistance will be the same as your earlier expressions, whereas your PMOS expressions, they are going to slightly change, that is in the linear region. As we all know, the linear region current expression is kW by L into VGS minus VD minus VDS by 2 into VDS. Fine. If I try to substitute the same, therefore, these are the currents and resistance expressions for linear region PMOS transistors. And in the third region, PMOS is in linear region still, therefore the same expressions are going to hold good, and NMOS is in off condition. As the NMOS transistor is in off condition, the current is going to be 0 and the resistance are said to be infinite. Let us try to represent them graphically. And this is a pass transistor, a transmission gate, and here I have introduced a large capacitance, and input changes instantaneously, whereas the output is going to change linearly. Fine. And this is the output voltage. As the time passes, the output is going to slowly change from 0 to VDD. Now let me talk in terms of current first. Fine. Up to VTP value, both the transistors are in saturation. Therefore, according to the expressions value, we will be having some finite amount of current, and as the output voltage is going to increase, the currents are going to slightly linearly decrease. This one and this one. And whenever we enter into the second region, and NMOS transistor will be still in saturation, whereas PMOS will be in a linear region. Therefore, in saturation we will be having higher value of current, and this is said to be linearly changed, constant, and whereas in linear region the current is going to vary linearly, but as the output voltage is going to change, let me show you the expression here. As the output is going to increase, this output value is going to increase, this difference is going to decrease. As this difference is going to decrease, definitely IDSN as well as IDSP both are going to reduce. and that's why your graph is like this. The current is going to decrease, and even the PMOS transistor current is going to decrease. And here the transistor is in linear region, therefore we won't be having a linear change. And in the third region of operation, where the output reaches just VDD minus VTH, NMOS transistor goes into off condition, therefore no current for NMOS transistor, whereas still the PMOS transistor will be in linear region, and the output is going to continuously increase, and that's how the current is going to decrease. Okay. And if you are going to have the sum of both IDSN and IDSB, and that is going to be like this. Now let me talk of the resistances, and let me again show you the resistance, and this is the expression, and this output is going to increase, and this output is going to increase, therefore the difference is going to reduce, and here we'll be having square of that resistance, it's going to be in reduced value, and accordingly we'll be having equivalent resistance for N. Okay. Therefore the denominator is going to reduce for your NMOS transistor, and that's how the resistance of the NMOS transistor is going to increase. And now let me talk with respect to PMOS transistor, and this is in the numerator only, therefore here Vout is increasing, therefore this difference decreases, therefore the PMOS resistance is going to decrease. That's how your graph is. PMOS resistance decreases, whereas your NMOS resistance is going to increase, and up to VTP. And moving into the second region, and that is between VTP and VDD minus VTH, and the same is going to continue, but the rate at which the resistances and currents are going to change, they are going to change. Why? Because the PMOS goes into linear region. Now let me talk of the third region. In the third region, PMOS enters into still in the linear region, therefore the resistance is going to change, whereas the NMOS enters into cutoff region, therefore the resistance seems to be infinite, and this is not actually shown here. And actually the equivalent resistance with respect to the transmission gate is said to be the parallel combination of both NMOS transistor as well as PMOS transistor. Therefore if we take the parallel combination of these two, Rn and Rp, it's going to follow this graph. And this is for the input changing from 0 to VDD. Similarly, we have the other case, still the output is going to have large value of capacitance, but the input is changing from VDD to 0. Fine. Therefore here also the output is going to slowly change from VDD to 0 volts. Therefore initially the output is having high value, and later it's going to have lower value. Accordingly the transistor operations are going to be slightly changed. Fine. And this operation is said to be similar to that of your previous case, but the PMOS and NMOS transistor operations, they are going to be interchanged. Therefore in first region of operation, both the transistors will be in saturation. In the second region, PMOS will be in saturation, whereas NMOS will be in linear. In the third region, PMOS goes into cutoff, and finally NMOS will be in linear region. And these are the three regions which are going to be partitioned by means of V output less than VTP, and the same condition, VDD minus VTP to VTN, and finally the output is less than VDD minus VTN. Of course you can consider the same expressions, you can check here. Input is changing from VDD to 0, and the output is also changing from VDD to 0, rather it's going to be a linear change. Check this one, from VDD to 0. Fine. And the graph seems to be similar, but the only difference is both NMOS and PMOS graphs will be interchanged. Previously this was IDSN and this was IDSP, but now try to interchange. And similarly this was Rn and this was Rp, interchange these two. Now let me consider the second case, where the output capacitance is said to be small. Whenever I talk of a low value of capacitance at the output outputs are going to change within less time. It's not going to take much amount of a time. Therefore, here also the output may change linearly, but the slope with which the output changes increases. Okay. Therefore, whatever the input we apply, the output is going to be nearly same as that of the input, but for a small change, a small difference. Accordingly, if you are going to substitute the values and so on, the PMOS and NMOS will be in the first region operation. PMOS will be in cutoff and NMOS will be in linear region. In the second region, both the transistors will be in linear, and then third region, PMOS will be in linear region and NMOS will be in cutoff. Try to observe this one. Your transistor never goes into saturation. In order to make the transistor to move into saturation, the condition is VDS should be greater than VGS minus VT, and that is not going to happen here. Why? Because as the capacitance is small, the output is going to closely follow the input. And therefore, for one case, I am going to consider the same. Input is changing from 0 to VDD. Therefore, output is going to follow the same chain, but for a slight difference. Okay. You can check the expressions. In the first region, both the transistors are in a linear region. As the transistors are linear region, this is the equivalent resistance. Therefore, V out, and this difference is said to be very, very small. Accordingly, let me talk in terms of resistance. This V out is said to be nearly equal to VDD. Therefore, this potential difference is said to be less. As this is less and this is going to be high in value, accordingly we'll be having a change in P resistance. Therefore, P resistance is going to decrease. Why? Because the denominator has increased value. And similarly, the NMOS resistance is going to increase like this. And in the last region, NMOS goes into off condition. Therefore, it's going to be infinite resistance. Therefore, if we consider the parallel resistance, it's going to take this form. Similarly, the currents, both the transistors are said to be in a linear region. Let me again consider the linear region expression like this. This V out is the same as VDD. Therefore, this difference is less and even this difference is less. Therefore, IDSP is going to increase. Therefore, initially PMOS is off, therefore 0, after which IDSP is going to increase. Initially, NMOS transistor is in linear region, it's having high value of current, after which it decreases, and finally in the third region, it goes into off condition where the IDS is equal to 0. Therefore, if you consider both the sum of both the PMOS current and NMOS current, it's going to assume this shape. And that's how we can analyze the transmission gate and how the resistances are going to vary. Let me tell you again. Simply you need to calculate the output, and you need to calculate VDS as well as VGS, and accordingly divide the operation of the transistor into linear, cutoff and saturation. Then try to write the current expression values and substitute different values of output in order to obtain the graphical representation.